To measure how acid or alkaline an aqueous solution is, we use the scale of pH. Most of the solutions we come across are in the range of 1 to 14, and there are different ways to measure pH, including indicator paper that will show a colour dependent on the pH. Alternatively, pH can be accurately measured using a calibrated pH meter. At room temperature, pHs of less than 7 are acidic, and those above 7 are alkaline. The precise pH when a solution is neutral, that is, it is neither acid or alkaline, will vary according to the temperature, but at 25 degrees C, the pH of neutrality is 7. pH is defined as the negative of the log to the base 10 of the hydrogen ion concentration. In order to change the hydrogen ion concentration to pH, we first take the log to the base 10 of the hydrogen ion concentration and then change the sign to obtain the pH. If there are 0.02 moles per decimeter cubed of hydrogen ions in an aqueous solution, we calculate the pH as follows. We press the log button on our calculator and enter in 0.02 and press equals. To get the pH, we then change the sign, and so the pH of 0.02 moles per decimeter cubed of hydrogen ions equals 1.70 to 3 significant figures. To go back the other way and convert pH to hydrogen ion concentration, we perform the inverse operations. We take our pH value and change the sign, and then we press the 10 to the power key. To obtain this function on this calculator, we first need to press the shift key and then this button. We then enter in negative 1.7 and press equals. Strong monobasic acids effectively completely dissociate into ions in aqueous solution, so the concentration of the acid equals the concentration of the hydrogen ions. And so to find the pH of the monobasic strong acid, it is merely a case of finding the log to the base 10 of the acid concentration and then changing the sign. And to find the acid concentration from the pH, we change the sign and then find 10 to the power of that number. When working with weak acids, because they do not fully dissociate into ions, the situation is more complicated, and this is where Ka values are useful, and we can use the equilibrium law to calculate the hydrogen ion concentration and consequently the pH. This is provided we know the concentration of the acid and its Ka value. Let's look at ethanoic acid. The Ka at 25 degrees C is 1.76 times 10 to the minus 5 moles per decimeter cubed, and we need to find the pH of 0.01 mole per decimeter cubed solution. Ka is given by. So in order to find the hydrogen ion concentration and consequently the pH, we need to know the concentration of ethanoic ions and the concentration of neutral undissociated acid. Since the ethanoic acid is a weak acid, we know only a small fraction of the neutral acid molecules will have dissociated into ions. We can therefore make an approximation that the concentration of undissociated ions is the same as the acid concentration, and so we can add in the labelled concentration of the acid for this term in the equation. Our balanced equation tells us that 1 mole of acid will produce 1 mole of hydrogen ions and 1 mole of ethanoate ions, and so, assuming there are no hydrogen ions from the water itself, the concentration of the hydrogen ions and the concentration of the ethanoate ions are equal, and so the top term in the equation becomes the hydrogen ion concentration squared. We now multiply both sides by the acid concentration and cancel, and we find the hydrogen ion concentration squared is 1.76 times 10 to the minus 5 multiplied by 0.01. We then take square roots of both sides and we find the hydrogen ion concentration is equal to 4.195 times 10 to the minus 4. To get the pH from the hydrogen ion concentration, we find the log to the base 10 and then change the sign. A 0.01 mole per decimeter cubed solution of ethanoic acid will therefore have a pH of 3.38. It should be noted that we have had to make an approximation stroke assumption in doing this calculation by assuming that the labelled acid concentration equals the equilibrium concentration of undissociated acid molecules, which for weak acids, with only a small amount of dissociation, is valid. However, for stronger weak acids, where the extent of dissociation exceeds 4%, it is not valid to make this assumption.